Hello.
Can you hear me?
Yes, sir.
Okay, thank you for your response. So wait 4 to 5 minutes, then we will start. Today we will discuss six assignment, and here is the 18 question. So today first question is this: the silicon solar cell has a band gap of 1.12 electron volt. Find the maximum wavelength for this silicon solar cell. These are four options. Please solve this question. So this is the first question of today. Please solve this question. The silicon solar cell has a band gap 1.12 electron volt. Find the maximum wavelength for this silicon solar cell. Maximum wavelength in the reference material can absorb the light. Beyond this wavelength, material doesn't absorb the light or incident photons. So please solve this question. Tell me the answer. Others, please. So let's discuss this question. Let's say have a material which can band gap is G. This is valence band. This is conduction band. If incident photon has energy h nu greater than or equal to Ag, then only material can absorb the light, otherwise not. So silicon solar cell has band gap. We have band gap 1.12 eV. Maximum wavelength, we know the E equal to, let's say E equal to band gap and Hc by lambda. So we have to find the minimum energy that can give maximum wavelength. So we can equate 1.12 eV at least. Incident photon has energy that much, then can absorb material, the incident photon. So Hc by lambda, you know the value of Hc, 1240 lambda in nanometer. This is eV in eV. To eV we cancel out. Then you can find out divided by 1.12. Please solve this. One 107.14 around nanometer in nanometer. So according to this, B option is correct. Okay. So tell me, let's say we have a spectrum. Here is a 400 to 700 nanometer, and here it around 200 to 400, 700, and beyond that. So this material, which side is absorbed? Let's say here is a 1107 nanometer. This side or this side? Which side this material can absorb the light? Left or right? This is left, right. Can silicon solar cell, yes, absorb beyond the this? Not, because energy has less compared to band gap, so material cannot absorb. So our solar cell, silicon solar cell, work in this wavelength. Okay, so clear this question. Can I move? Second question. The approximate thickness in microns of the absorbed layer in a monocrystalline silicon solar cell. These are options. Okay, others please. So this is answer C is correct. 300 nanometer thickness of monocrystalline silicon solar cell is sufficient to generate electron hole pairs efficiently. Next question. The extract power from a solar cell can be maximized by. These are the options: minimize shunt resistance, maximize shunt resistance, minimize series resistance, maximize series. There are series and shunt. Extract power from a solar cell can be maximized by. You know the RV characteristic of solar cell. This is the J. This is the V voltage applied. This is a current B and C. Maximize the shunt, minimize the series. And others, please. So we know the ideal curve. Let's say this is VOC, JSC. This is rectangular is ideal. Perfect squareness give 100% efficient solar cell, but we don't have. If the losses is zero, so which side is series and shunt? This side tangent, inverse of tangent give shunt resistance. This side is series. Okay. This side is series. So power actually I into V, area under the curve Q of power. Area under the curve give to power. So when power is maximized, in the ideal situation, this is rectangular. The shunt is infinite, the series is minimum. This size is inverse of the IV. This solar cell characteristics tangent at VOC, reciprocal at VOC give series resistance, and tangent at JSC. Reciprocal of tangent at JSC give us shunt resistance. So you can see if shunt has maximum, series is lower, so give us maximum area. Then we can extract maximum power. Okay. So let's show you two result. Maximize the shunt resistance, minimize the series resistance. Please look at these three IV characteristics. This is the lab result. Are you able to see? So when we minimize the series resistance, maximize the shunt, we get more power. Can you compare which one is better due to best efficiency? These are in three curves: 300, 4000, 3000, 4000, 5000 RPM. This is a coating parameter of a spin coater. Which cell? 300. Yes, because here is the area is maximum, so we can extract more power. Clear to you? So please look this also. This is the solar cell circuit. You can see shunt or series. Please look this curve and also the circuit. So you can see in picture as central resistance represented by RS and series resistance is central resistance SH, RSH. Here is also mentioned series resistance RS only. And this is in central resistance is parallel while the series resistance in series. And we have to extract power from here. So please look this circuit. When we get more power, central resistance should be infinite. Otherwise, our current is also come from here and here. If the central resistance is high or infinite, our total current is follow this path. And why series resistance is low? Because some losses is also here in heat form or something else. So series resistance is should be 0 and central resistance should be infinite. You can see from the circuit representation. Clear? And please look also this curve for ideal solar cell is this condition. First, this is second. Here is explain the series resistance. There is a shunt. Here you can see the shunt resistance is high and is tan theta. Please look the tangent. Here is a look like. So when we move this side, center resistance is small to high, very. Yes. In first IV characteristic, series resistance. Look here when we take the tangent. Reciprocal of tangent IV curve give to us resistance. So also remember the order from where to where is small or high. So is this side is large, then medium, then small. Series resistance is getting large to small. So clear to you? For ideal solar cell, please remember the curve should be like that. Rectangular shape. Sun is, this side is sun is infinite. This side is series is tends to 0. VOC side give series resistance and JSC side shunt resistance. Okay, so let's move the question. Yes, solar cell have having band gap of Ag1 and Ag2, and Ag1 is higher than 2 Ag2 are eliminated by one sun irradiation. Then which of the following is expected to the true? Consider only the optical losses. Please solve this question. This is a multiple choice question. Please, one from here and one from here. And why? So please, others, please give answer. And JSC, so look the answer. P and D is the correct option. And please look here. Band gap is directly related to the VOC. If band gap is higher, then VOC is higher. So band gap first is higher band gap, so VOC is higher. But in the case of current, order is reverse. And why? So let's show you. This is Ag1, Ag2. Ag1 is higher as compared to Ag2. When illuminated by one sun, let's say same light of photons, which one is get more lights, Ag1 or Ag2? One sun has all spectrum range, let's say 200 to 800, 900 or 1200. Which material get more number of photons, Ag1 or Ag2? A spectrum of light, visible and X-ray, infrared. Which one is get more light, Ag1 or Ag2? Ag2. So we can see if the material wavelength has, let's say, first this is Ag1 and Ag2 lies somewhere here. So first is absorbed from air to this side, while the second is also left side, but get more number of photons absorbed. This much number of photons get more absorbed by Ag2. So if we have more number of photons, let's say material get more number of photons, absorb more number of photons, then excite in the material in the solar cell, excite more number of excitons and give more number of electron hole pair. More number of electron hole pair. If electron and hole pair is higher, then current is, let's say, I. If number is high, then current is high. So are it clear? If the band gap is less as compared to the other material, then get number of more photon absorbed by less band gap material and give number of more photons absorbed and excite more number of excitons and give to us more number of electron hole pair and current is high. Clear? So D is also correct. Next question. Sorry. Shunt resistance in the solar cell can be increased by, we have to maximize shunt and minimize reach. So which parameter can improve our shunt resistance of the solar cell? What quality of solar cell should have? Please choose the right option. Yes, please. So B and C are the correct options. Defect density related to the shunt resistance, also non-additive recombination. What is non-additive recombination? Recombination by shallow trap levels is happen then that give us non-additive. For shunt resistant band-to-band transition, jump ahead where is EV is C. But in between shallow traps or deep traps also there a transition between there. So shunt resistance is less while air shunt resistance is high. So shallow traps or defect density surface defect density also matters shunt resistance. If pinholes in the film, let's say, so our device is shunt, so defect density also matter, should be has less defects, should not be there is a pinholes like, and non-radiative recombination also. We have to also reduce the non-radiative recombination for efficient solar cell. Okay, next question. Which of the following is correct for ideal IV characteristic of solar photovoltaic device? We have already discussed. Please choose the right option. Sorry. Yes, please. Which option is correct? Let me tell you. Let me give to you hint. This is IV and JSC VOC. This is J. This is V. Divided by GV inverse equal to resistance. This is int. Now please solve. Please choose correct options. This is nothing but tells about the resistance. This question is about resistance of IV characteristic. Inverse of slope of J curve give the resistance. So please choose two options at JC v equal to 0 and R v equal to VOC. So we know this side is shunt resistance. Shunt resistance should be infinite and series resistance should be 0. So which option is at v equal to 0, v equal to 0, infinite, and VOC v equal to VOC equal to 0. Okay, clear to you? Next question. Which of the following statement is correct for the polysilic polycrystalline silicon in comparison to single crystal silicon? Yes, please. Single crystalline and polycrystalline silicon. We have to compare. So two option is correct. Polycrystalline has higher defect density and also a smaller Callier diffusion length. In polycrystalline, defect density is high and also smaller the carrier diffusion length. I think sir is discussing this in class lecture. Please follow the lectures also. Okay, let's move to the question 4. Yes, in a top illuminated solar cell, light coupling can be enhanced by, let's say, this is top side and light incident from top side. So coupling of light to the material can be enhanced by, let's say, bottom layer, top layer, absorbable material, also anti-reflecting coating, texturing, texturing, and anti-reflecting surface. Please choose. So only C and D is correct. For solar cell, these are two techniques for enhance the light coupling are generally used: anti-reflection and texturing from the front side. These are not correct. Please follow the lecture. I think sir is discussed. For any solar cell, if we have to enhance the light coupling, so we can generally use anti-reflection and texturing at the front side. Next question: which of the following is are favorable for efficient solar cell? Yes, please. So C and E option is correct. Favorable efficient solar cell. Diffusion length obviously is high for minority charge carrier, and E, large built-in electric field. This is not about the solar cell. This is not about the NPN transistor. This is about the solar cell. Okay. Next question. Which of the following strategies are adapted to improve the current location from top of silicon solar cell? Strategy are adapt to improve the current collection from the top the silicon solar cells. We have to improve the number of more electron hole pairs. So which strategies are used? Deeply bared contact and heavily doped near contacts. Okay. Yes, the correct sequence for the generation of electricity in solar cell. Please choose the order. How solar cell is work. Right. 1 minute. Yes. Which option is correct? How solar cell is work? Please choose four steps. Which one is first, then second, then third, then fourth? So D is correct answer. First, light is absorbed, then create the exciton, then exciton diffusion, then diffusion of charge carrier to electrodes, and collection of electric charge carriers. The method is adapted to reduce the surface recombination in silicon solar cell is a yes, please answer the question. So B and D is correct answer. For surface recombination, we have to also passivate the surface and heavily doped rear surface of the cell. This is about the surface recombination. Previous question is about the shunt resistance. Sorry, previous question. We have already discussed this type question. Yeah, light coupling. This is for coupling lights, and this is recombination about. Next question, please choose. Please give me 1 minute. So, which option is correct? Incorrect, sorry, for the multicrystalline silicon solar cell. So option A and D is incorrect. Large number of grain boundaries and grain size is smaller than the device thickness. So what is the question? Okay, which of these are incorrect for the multicrystalline silicon solar cell? So larger number of grain boundaries, this is should be correct, but this is incorrect. And grain size is larger than the device thickness. So this is incorrect and other are correct. And also low number of grain boundary, high number of grain boundaries, larger than the grain size larger than the device thickness. So multicrystalline number of, let's say, grain. So stab metal number of, larger number of grain boundaries. This is a grain and these are grain boundaries. So for this is, let's say, which of is are the for correct option for multicrystalline solar silicon solar cell. So larger number of grain boundaries and grain size is larger than the device thickness. Grain size is smaller than the device thickness. So we know that generally device is made of the material. If the grain size is, let's say, this that much, and this is device thickness, let's say. So grain size should be smaller than the device thickness. So grain size is smaller, should be smaller than the device thickness. These are correct. So this is incorrect option. And low number of grain boundaries. Larger number of grain, large number of grain boundaries should be there for multicrystalline. So B and C are incorrect, while A and D are correct. Okay. So this is, please correct this question. Which of the following is are correct for multicrystalline silicon solar cell? Okay, next question. The passivation of the Danling bonds in the amorphous silicon solar cell is done by which technique is used for Danling bond passivation? How we remove the Danling bond? So hydrogen passivation. Yes, correct this option. Next question. Silicon nitride coating on the emitter in a polycrystalline silicon solar cell is done to.
So what was the last question?
Sorry. Yes. The passivation of the dangling bond in. Sorry, my screen is not visible. Yeah, this is the last question. The passivation of the dangling bond in the amorphous silicon solar cell is done by hydrogen passivation. Yes, please. Can I move?
Yes, sir.
Okay, thank you. Think my internet is slow. Yes, next question is silicon nitride coating on the emitter in a polycrystalline silicon solar cell is done to. Why we have coat silicon nitride on emitter? So we have to reduce the reflection losses. Okay, next question. Yes, please. This is the numerical question. These are four options. A solar cell deliver a short circuit current Js equal to 7 ampere under 1 AM 1.5 elimination. The reverse saturation current J naught 10 to the power minus 11 ampere. The open circuit voltage we have to find VOC. Neglect the any internal resistance of the cell would be. Please solve this question. You have a 5 minutes. Please take 5 minutes. Solve this question. So, which option is A is correct? So, please see the solution. So this is the formula we have to apply. VOC equal to KT by Q ln JSC by J naught or ISC by I naught plus 1, and KT by Q at room temperature or at 300 Kelvin equal to 0.0 around 26. So please put these values and okay, I think all is get answers. Next question. Yes, please. This is also numerical question. Typical absorbed layer of crystalline silicon solar cell absorb 43% of the light of wavelength 1100 nanometer incident from the AM 1.5 illumination, assuming that the absorption coefficient for the infrared light is alpha is 10 centimeter per centimeter. The approximate thickness of the absorbed layer is. We have to find the thickness of absorbed layer for crystalline silicon solar cell. You can also take 5 minutes for this question. Yeah, you can use this formula. I naught e to the power exponentially alpha d, where d is the thickness of the layer. Now please solve. So yes, typically absorb layer of crystalline silicon solar cell absorb 43% of the light of wavelength. So I equal to 43% of I naught. We have to give. You have to given. Now please solve. Okay, so please look I equal to I naught 1 minus, sorry, 1 minus. We have to write wrong formula. Formula is this 1 minus exponential minus alpha t. Now please look. We have to already given I by I naught equal to 43% and this is divided by 43%. So and alpha is given 10. Put the alpha. We have to find thickness T or D. So now please solve this exponential term. And these are the steps. This is first, second, then third, fourth, fifth, sixth, seventh step. These are given parameters. So from here to here, last step. We have to also convert in micrometer. These are given parameter. Okay, got it? Others, please. Okay, thank you. So this is last question. Please solve this question. The silicon solar cell has band gap 1.112 eV. Find the maximum efficiency of the silicon solar cell if incident photon has wavelength 1300 nanometer. Others, please. And why is 0? This is a fundamental question. We have already discussed this question. So our band gap has material 1.12 eV and incident light has less. H nu is less energy as compared to 1.12 eV. So our solar cell doesn't work, cannot absorb. So if material is not absorbed, then efficiency is 0. So what is the energy of incident light? Please find 1240 divided by 1300 nanometer. This is in eV. 0.9538 electron volt. This is the incident light of photon having energy 0.953, but our material has band gap 1.1. So material cannot absorb this light. So if material doesn't absorb, doesn't give any efficiency, no electron hole pairs, no excitons. Okay, so answer is 0. So this is last question. Okay, thank you. Thanks for your kind attention and interaction. Thank you. Thanks to all of you. We will meet next Monday.